Just realized, so I'm recording this, by the way, but I didn't have sound on the first two slides, so there's not going to be any sound. The actions themselves should be here, but unfortunately there wasn't sound. The microphone was on mute. So I can do this. I can do that if I want, and that's a correct answer technically. I think of this as a coefficient for k and just divide by it. That's one way to write it. Or you can multiply by 4 pi squared to bring that up, and then divide by tau squared, which will get you up to here in this answer. Okay? We will practice more of solving for variables contained in radicals. We will definitely do more of that, so you'll see more of it done. I know that this was not like the easiest type of problem, but this is the type of problem that you will end up doing throughout the year when you solve for a variable contained inside of a square root. Okay? All right. So if you look at this later and you want to relook at all the stuff that's on here, I hit the microphone now, so now you hear me talking. All right. Slide 3 or page 3. These are just trig functions. So your basic trig functions. You should know SOHCAHTOA. If you don't know what I'm referring to, you got to really brush up on your work then. Okay? You should know the acronym, SOHCAHTOA. So if I want the sine of an angle, I take the opposite over the hypotenuse. So sine of theta equals what? Sine of theta equals? Yeah, 3 over 5. Okay, opposite over hypotenuse. That's the sine of theta. That equals 3/5. The cosine of theta equals? Good. Adjacent over hypotenuse, or 4/5. And last one? Good. Opposite over adjacent. 3 over 4. That should have been guaranteed for pretty much everybody. The other stuff coming up could be a little bit tougher, but you should be able to write your trig ratios based on your geometry course. Second, or fourth, whatever number this is. Determine the length of the unknown sides in the triangle shown. So now we're not writing trig ratios, but we're trying to solve for unknown variables in the problem. So how would I do so? If I want to figure out what x is in the first diagram, what can I write? Or if I want to figure out what y is, what can I write?
The sine rule, like sine
Good.
35 over y equals sine 90 over 7.
Oh, you're doing law of sines. That works. Law of sines or law of cosines works, but it's a right triangle, so you don't use law of sines. That's too much. You could use Pythagoras if you had 2 of the 3.
Yeah.
Make it basic. You're doing way too much work for yourself. So he's talking about law of sines, where if the triangle is not a right triangle, you use law of sines or law of cosines. You're going to learn about it in your pre-calc honors course this year, actually. So because it's a right triangle, we don't need law of sines or cosines. So what would I write instead?
Cosine 35 equals x over 7.
All right, we can start with cosine. That works. So then sine of 35 would equal y over 7. Everybody see that? Sine of the angle equals opposite over hypotenuse. Cosine of the angle equals adjacent over hypotenuse. That's where that's coming from. Now, if I want to get x and y by themselves, I just multiply by 7. This becomes 7 sine 35 equals y. And this becomes 7 cosine 35 equals x. And those will have decimals. X is 5.7 approximately. X is around 5.7. And y is around 4. Was it 4? 4.1? What was it? 4.02. So it's pretty much 4 for y. Okay, so x turned out to be, again, 5.7. And y turned out to be around 4. You know the difference, right? The symbol means around, approximately. Okay, circa, approximate. I'm going to leave part B for you to practice if you need a little more practice on that. But the answers for part B, x turns out to be 11.7, approximately. And r turns out to be approximately 17.5. Okay, that's for part B in that diagram. But I'll leave that so you can practice part B if you didn't understand it for some reason. You have A now. Number 5. Hey, what's the difference between number 4 and 5? What's the difference between numbers 4 and 5?
In number 4, you're solving for a side. In number 5, you're solving for the angle.
And whenever you solve for an angle, what do you have to remember? What do you have to remember to utilize when you solve for an angle itself?
Like you have to press a second and then the negative sign.
Do you remember the calculator? It's second, right? It was called the sine what? What was the word for it? Sine, cosine, or tangent, you put a word after them though to indicate you're using sec.
Inverse.
Inverse, very good. So it's the sine inverse or the cosine inverse that allows you to solve for an unknown angle. So to solve these problems though, we have to recognize that we have to start with a ratio. What ratio is shown here? If I've got the opposite side, not the adjacent, I've got opposite and hypotenuse, sine. So for this one I've got sine, whoops, zoom in. I've got sine of theta equals opposite over adjacent, opposite over hypotenuse. And if I want to get theta by itself, I take what's called the sine inverse of both sides. Take the sine inverse of both sides of the equation. The sine inverse of the sine of theta, what's theta? It's the idea that the function cancels. So we get theta equals the sine inverse of 4/7, which is again approximately 34.8 degrees. I will leave part B for you to practice if you struggle with part A. All right, the answer for part B, though, is 20.6. The answer for part B is 20.6 degrees on my units. You're going to learn about other types of units for angles this year in your pre-calc course. You guys have missed a few already, right? Yeah. You're going to learn about other types of units. They're going to be called radians later in the year. It's not any more difficult. It's like inches versus centimeters. Radians are another type of angular unit. That's all they are. Like degrees are 360 for a circle or 180 for a semicircle. Radians are represented in terms of pi. 180 degrees is called pi radians. 360 is called 2 pi radians. You're going to learn about that this year. So for the sake of physics, we're going to have everything in degrees. Everything's going to be in degrees, not in radians. And if you look at your calculator right now, folks, hit mode. You can take out your TI, whatever you have. If you hit mode on your calculator, make sure it's set on degree mode and not on radian mode for this course. When you're in your math class, you might have to go to radian mode at times. So again, try to do this now so that you understand where it is in your calculator. Hit mode, and then make sure that degree is highlighted. If it's not, go to degree and hit enter on it so that it is on degree mode. I'm going to keep moving. I'm going to assume you're doing this as I say it, but I'm going to keep moving. So if I look at part 6 now, if I look at part 6, the only difference is part 6 just wants me to find every side and every angle. Right? Determine all the angles, all the sides. So for this problem, it's easy to get the third angle because what do 3 angles have to add up to? 180. In a triangle, 180. So I know that already this must be a value of 62 degrees. 62 and 28 gives me 90, and here's the other 90. So the third angle is easy. You don't need trig at all. Right? No trig whatsoever. It's just arithmetic. To get these other lengths, though, we're going to have to use trig. And once I get this length, what could I use if I have 2 sides? What can I use if I have 2 sides? Pythagorean theorem to get the third side. So whether you use trig twice and use trig once here to get this number, and then use trig again to get this number, that's fine. Or once you get this one, use Pythagorean theorem. It doesn't matter. You choose. The answers are as follows, though. This is, the hypotenuse is around 10.6. The base is around 9.4. And again, this is 62 degrees. Okay, that's what you'll get for answers. But again, I'm not going to redo all these problems. We just did it in numbers 4 and 5. Okay, it's the same approach you would take as numbers 4 and 5, but you have to get everything. Part B, the answers are 9.7, and you can get that very quickly with Pythagorean theorem. You could then get one of these angles using trig and using an inverse function to get the angle, and then you can get the other angle by adding up to 180. Okay, so those are your 3 values for the answer for part B. Any questions so far? Okay, move on, next page. So you guys, obviously you're in an honors course, so you'll recognize that I'll do a lot of this. I'll go over work, I'll give you credit for the work when you submit it, but it's on you to recognize whether you understand it or not. For example, again, I'm not going to be checking that this is right or wrong. So if you just turn something in that has all wrong answers, you're still going to get credit, but you're not going to benefit from that at all if you don't go back and relook at the work that you got wrong. So you need to take it upon yourself this year to make sure that you're advocating for yourself and that you're like self-assessing throughout the year. Okay? And if in doubt, you come see me about stuff that you don't understand. Number 7, the solutions are going to be, or the solution is 4, comma 2, which means x is equal to 4 and y is equal to 2. Okay, which method would you use? I asked you to use substitution here specifically because in physics you're going to use substitution a lot. You're rarely going to use elimination. You will use it eventually, but you're rarely going to use the elimination method, so that's why I indicated to use substitution method. And remember how substitution method works? You take the quantity that's equivalent to one of the variables and substitute it into the other equation for said variable. Okay, so 2x minus 6 is y, so plug that in there. Make sure you distribute the 2 to both of these terms. This is going to go in for y inside of its own parentheses. That's the one mistake that a lot of students end up making. Okay, again, when you plug in for y, it's going to be this 2x minus 6 in its own parentheses. So this would be the equation here, boxed in, that you would end up solving. Okay? That's the equation you would end up solving to get x. Once you get x equals 4, plug a 4 in there. 2 times 4 is 8. 8 minus 6 yields 2. Substitution method. A was an easy one. B was a little tougher. Not much, but a little bit tougher. So I would substitute right in again, and you would end up getting an x value of 4/5 and a v value of 2/5. Okay, 4/5 for x and 2/5 for v. And this one is set up in such a nice way, God bless you, that I would take x over 2 right here and replace v with x over 2, and then solve the resulting equation. Yeah. Any questions on part B? On part B right there. Okay, part C. Part C was a little bit trickier. Okay, a little bit trickier, and you're going to see why that is. You have multiple answers for part B, actually. There are multiple answers. So F is going to be plus or minus 1. F turns out to be positive 1 or negative 1. And N turns out to be positive 1/2 or negative 1/2. So when F is equal to 1, N is equal to positive 1/2. When F is equal to negative 1, N is equal to negative 1/2. Yeah?
How do we know when to do plus or minus or just leave it?
So let's go through this and I'll show you for this one. So we've got F equals 1 over 2n and F over 2 equals n. We could substitute this either way we like. We could take this expression for n and plug it in there, or take this whole expression for F and plug it in there. I'm going to choose to plug in from this into the first. So I'm going to take F over 2 and plug that in for n. So I'll take this quantity right here, because it's defined as n, and plug it into the first equation. And the first equation becomes this. And then the 2's cancel, and then this equation becomes f equals 1 over f. I have to multiply both sides by f. It becomes f squared equals 1. And then because I'm taking a square root, f is plus or minus 1. It's the square root that you take that is what yields the plus or minus. Okay? So again, this is the process you would take. And that would give you the answer. Not ignore, but try to section this off. Okay? That answer is in the box, but the work is all shown along the entire bottom. Questions on C? Questions on C? I'm doing on time. Number 8. Number 8 was only confusing because you're not getting an answer as a number here. You notice for number 8, your answer is not a numerical final answer. It is an algebraic answer. So it says, solve for t in equation 1. What do you get when you solve for t in equation 1? Regina?
X over v.
T equals x over v. I agree. And then substitute that into equation 2. Here's equation 2. Okay? Notice I like to use colors. You picked up on that by now to show substitutions. I recommend that for yourself as well. If you're doing several things in a problem, having color coding systems really helps to see it in your notes like a week from now, right? When it's not fresh in your mind. So consider that. Now, at this point in time, what our goal is to solve equation 2, which is this, for v. And look where v is, right? So this becomes a little bit messy to get v by itself. So let's go ahead and do that. So to get v by itself, here's what we're going to do. We're going to recognize the following. If a were a number, this would be a coefficient, and you would just divide by it. So you could divide by 1/2 a to start to get rid of it in front. You could also multiply by 2 to get rid of the 1/2, and then divide by a. Again, either way works. So if I start this problem, I could say, okay, I'll multiply by 2, and I'll divide by a at the same time. Multiply by 2 and divide by a at the same time. Well, this 1/2 cancels with this 2 by multiplying. This a cancels with this a. So I end up on the left side with 2x over a, and the right side just x over v quantity squared. So this is what I've got so far. Now again, what is my goal? My goal in these problems is to figure out, or in this problem, what the value is for v, which is down here. What do you recommend I do at this point if the value for v is down there? What are you thinking?
Take the square root of both sides.
Yeah, at first I would think the same thing, Mauro, but there's actually another way to approach this one that's probably a better route. I would normally think that. Yeah, and we'll discuss why in a moment, but I would square everything first, actually. So I make this 2x over a equal x squared over v squared. And the reasoning for this is because now one of your x's cancels out, and you're left with an x over here. If you square root both sides first, you end up with a square root with an x in it, and then you have an x over here, and it just becomes messier. It would still work, but this root is more optimal to take. Okay, it would still work, but this is more optimal. So this equation reduces to 2 over a equals x over v squared. I want to get v by itself. I'm going to multiply by v squared on both sides, making the left-hand side v squared times 2 over a equals x. Then I want to get rid of 2 over a. So to get rid of 2 over a, I'm going to multiply by a over 2. And then finally, the last step, I'm going to take the square root. Okay? So that's my final answer. X times a over 2 underneath the square root plus or minus. A lot of work to get a simple solution, or what seemingly looks simple, but it's a very powerful solution. We're going to talk about power in physics as a solution being powerful. Jeff?
At first I did the same thing Mauro said, where I would have just square rooted the whole thing. If you just left it like that, would that be correct, or do you have to?
Yeah, the problem is that you would end up having stuff with radical x and x in the answer. Is that what you had in the answer?
Yeah.
Read me your answer, Ken.
I erased it, but
What do you got? What does it become?
I erased all of that. It was x and then x in the radical.
Yeah, so you end up with an x and a radical x in the answer, which is okay, but it's more traditional to have only one, have that variable only appear in one spot if you can. So if you have x over radical x, it becomes radical x in the end.
what does radical mean? Sorry.
Square root.
Okay.
Square root. The symbol is called a radical. The thing underneath is called the radicand.
Oh.
So I'll use the phrase radical a lot to indicate square root.
Sorry, I just wanted to.
Yep, I know, nomenclature, I know. We were talking about that, yeah. Okay. If this problem was the one that you really struggled with, that's okay for now. For now, that's okay. But as we progress through the year, you should be able to solve a system of equations with only variables. Okay? It's all right for now if that was one struggling point, but if you really had trouble with this, I'd recommend being after school today to practice a couple more of these with me. Let's take a look at these two here. Well, actually, I might pause. Where are we at? Yeah. Let's pause on the summer packet for now. We'll start these up in another class because I don't want to spend the whole period doing this. It gets boring after a while. So let's stop for a moment. What I'm going to do is hand out the lab to start now. This is one of the simplest labs of the year. It is very rare that a lab is only front and back. This is really more of like an activity than it is a lab, to be honest. Okay? And the rationale or the reason behind this is that I want you to become accustomed to taking good measurements and to understanding your measurements, and then also taking data and being able to graph that data and understand the significance of the graph. So this is really very little physics. It's more like, again, a lot of the math you need to know for physics. So the premise of the lab is the following. It's called the circumference diameter ratio. The circumference diameter ratio. I'm going to give you a bunch of circular objects. I want you to measure the diameter, the circumference, and the height. They're going to be cylinders. I want you to measure the diameter, the circumference, and the height. I want you to measure in centimeters. I want you to read the directions because they tell you the nearest tenth of a centimeter. But read through all of them anyway, giving you a summarization. Then once you have diameter, circumference, and height for your 6 objects, which are numbered, you then are going to plot circumference versus diameter on the next page. You're going to plot your table of values. Please remember, if something says circumference versus diameter, it means circumference is on the y-axis. Diameter is on the x-axis. Is that clear? Okay, the circumference is a function of the diameter. If you have a bigger diameter, you have a bigger circumference. So it's going to be circumference versus diameter. Your diameters might only be up to like 3 centimeters. Are you going to make this 1, 2, and 3 and only use this part of the graph right here? You better not, right? So you need to think logically. You can make your increments on the x-axis go by like 0.5. And your increments to the y-axis can go by 3, 4, 7. You can make them different, but they need to be consistent on that axis. So if I do every box is worth 1 on the x-axis, that's fine. And then every box is worth 3 on the y-axis, that's fine. But I need to be consistent in my increments along each axis independently. Okay? But they don't have to be the same increment. I don't have to go 3s and 3s here. So you're going to graph that, you're going to plot it, you're going to calculate your slope, you're going to draw what's called a line of best fit. A line of best fit does not go through every data point. It is just a line of best fit. It goes not through all the points, but it goes in a certain way, this is too perfect, where it kind of aligns with all the points. But for example, if you had points here, here, all around, the line of best fit would kind of go through most of them. But you do not connect the dots. You do not connect the dots. A line of best fit is a linear function in which you will calculate the slope. Once you have your line of best fit, you're going to take 2 coordinates on the line, not necessarily your coordinates, but 2 coordinates that are on the line that maybe match up with one of your increments or where the grid lines meet to make the number nice and perfect, and then calculate the slope. And then simply answer a few questions. Very, very easy lab. Very little extra conclusion that you have to do. Okay, it's not a good example of the level of difficulty you can expect going forward. That's all I want to make clear. Okay, so don't think like, oh my gosh, physics labs are so easy. This is a very basic lab on math concepts that you really need to know. Share. Here.
I only printed the sheet last night. What can I turn it into next class?
You talking about the summer packet or the syllabus? Which one?
Summer.
You can turn the summer packet in anytime before the first test, as long as you get it done.
Alright.
So again, I'm just going to check that you did. I'm not even going to grade your stuff.
Oh.
So if you show it to me like after class, I'll mark it off my grade book as done. It's on you to understand it.
If I have an opportunity, yeah, because most
Yeah.
of the stuff I got.
Yeah.
So if I have an opportunity this class, I just finish it quickly.
Yeah, if you finish the lab first and stuff, that's fine.
Alright.
All right, so let's quickly hand out the supplies for this. So your supplies, you got 15 minutes. So in the 15 minutes, I recommend trying to get your measurements down. Okay, trying to get your measurements down. We have a lot of students in this class this year, which is awesome. I love having a lot of students, but it's tough with labs sometimes for groups. So I might have you in groups of 3 or 4 at times. I prefer not to, but for this lab, it will definitely be groups of 3 or 4. So we have 4, 8, 14, 20 that is starting. So there are 21 in the class, so it's usually going to be like 7 groups of 3 most likely for the year. Okay? So you're going to have a bunch of different circular objects, cylindrical objects, and they have numbers on them. Okay? Everybody should have numbers 1 through 6. I think I have 6 sets of them, so we might end up sharing stuff. But you should look for objects 1 through 6. Okay? So I'm going to start by putting some here. And a little bit. 1, 2, 3, 4, 5, 6, 7, 8. So let's see. Yeah. So why don't we do up to Valentina, the 3 of you. Valentina, why don't you slide over with Regina and Julie over here. You guys can do these right here. Francisco, ruler for each group, please. Next. Just take a ruler to each group. So the two of you guys, Moro, come slide up. Work with these guys up here, please. Just get this. How many did I give you guys? So Moro, you're with these guys over here. This is going to be 3 and 3 in the middle area. I cut all these things down, so I'm not all exactly. Buying this stuff. The lab, buy something for like $800. Spend about $20 if you can see it on people and design myself. It just shows you that like it's ridiculous. It's up to you to choose, listen, it's up to you to choose whether you're going to measure the diameter from the outer parts or the inner, but then your circumference has to also be that way down. So think about what's easier. I'm going to come around and I'm going to give every group a piece of string. You're all going to get a piece of string. Centimeters, 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 centimeters. Where are my keys? These are identical. I think this is number 1. That's number 2. And 3, 4, 5, 6. So you should have all. You should have all. Again, guys, you're measuring. You're not calculating. Careful. You are not calculating right now. You're measuring. You're measuring. Do not use 5 times diameter to find that circumference. You're only measuring right now. You are not calculating. Your redirection is. I guess I'm measuring that. That's safe, right? Feet to the nearest 10, it says, right? What's the direction? Redirections, redirections, redirections. Those would be the 2 points that I'd be choosing, or maybe the starting point and the middle point. But every other point along the way is kind of in between hash marks, right? It's not at one of our grid line intersections. So that would make the most sense to choose these. And I can think about my slope as delta y over delta x. My change in y here is going to be 15, it looks like. My change in x here is going to be 50. So we have a change or a slope of 15 meters over a time period of 50 seconds. So when we look at this kind of graph, we're recognizing here that it must be moving at a constant rate, and my units of meters per second represent what? What's the word in physics we might use? We haven't used this term yet, but we've used it in math. Objects what?
Rate or unit.
Yeah, but in physics, in math you use rate. It's another word for it. We're going to start using. We haven't talked about that. Yeah, velocity. Very good. So the object's velocity rate is the same thing. We're going to use the phrase velocity here.
Wait, isn't the change in x 25 seconds?
It is 25 seconds. Thank you. So we have a rate of what looks like 0.6, I guess, right? 0.6 meters per second. Thanks, guys. Please don't feel like it's weird to tell me I'm wrong on something. If I ever copy something wrong, I'm going to do this real quick. Right, it's definitely 25 seconds. Thank you, Eduardo. So 0.6 meters per second. 0.6 meters per second. So what does that mean physically? A step, a big step is about a meter. This is a meter, each step. So if you're going 0.6 meters every second, it means that your step is not a full meter every second. It means that you're stepping about 0.6 of a meter every second. So this is the rate. You need to get number sense through your head also. So throughout this course, you're going to recognize, I'm going to pick up that, I'm going to say values and say, what is the significance of that value? What does it physically mean to you? So 0.6 meters per second, you should be able to visualize what that is. Base it off of 1 meter per second, this being your step length, and instead go to about 0.6 meters every second. Okay? Anything else about this one? No. Okay. I'll have a follow-up question though before I go to the next one. What if it weren't a line? What if it were a curve such as this? What would that tell me about the motion of this boat in this problem here? Isabella, what are you thinking?
And speeds up.
Yeah, it's speeding up. Because in the beginning, it's not covering much distance vertically. You can see there's no real change this way, yet time is elapsing. So the boat engine is starting. Okay, it's starting to move from the water. It's picking up speed. It leaves the inlet. Is that what it's called? The inlet where the boat's off to run very slow. It leaves the inlet, and then it really turns on its engines, and then it starts moving. And maybe it goes at a constant velocity after that, and maybe the line is straight afterward. But maybe it's still curved. Yeah.
Well, since it's an exponential graph that curves upwards, at first the gradient is flat, so that means it doesn't go super fast. And then over time, it increases the gradient, which means it keeps
Slope,
going faster.
yep. So it's the same word. So using the word gradient, slope in this case. So the slope of what's called the tangent line keeps getting steeper. Very good. Good analysis there. So the idea is that we can determine an object's velocity, and we're going to see this in chapter 2 more, by the slope of the curve of the tangent line to that curve. Remember tangent in math was a circle, and the line touched the circle once on the very outer edge? Same concept here, tangent lines. So that's the tangent line at this point. Well, then at this point, that's the tangent line. At this point, that's the tangent line. So what Jack is saying is that the slope of the tangent line is increasing, which means that the object's velocity is increasing. We're going to see again that in chapter 2, but again, the units help me to see meters per second. This must be velocity. Good analysis there. Very good. All right, how about the second one? Let's see if we want to go over this or maybe... Oh, no, we will go over this one. How is this one different? Let me start that question than the previous one. How is it different than the previous example? There's one major difference right away.
Because the units are velocity and time.
The axis labels are velocity and time. So this is not a position time graph. This is a velocity time graph. Velocity time. So verbally, tell me what's going on here. Verbally, what's going on? And we'll get to other ones. Jack.
The boat's getting faster by a constant rate.
Yeah, the boat is increasing its velocity, and that increase is consistent or constant the whole way through. Again, this is a very different graph. Here's how I say it to myself, right? I would say, well, the velocity is 1 at the beginning. The velocity is 2 after 1 second. The velocity is 3 after 2 seconds. So that's my numerical representation of that. I'm looking at my data points to see it. But verbally, the velocity itself, which is this function, is increasing. In the last example, the velocity was constant because that was a position time graph. But here, this is a velocity time graph. Now, if I were to find the slope of this, what's the number I get for the slope here? What do I get more?
2.
1/2. It's no problem. So every time we go up 1, we go over 2. So 1/2, right? 1/2 is the slope.
The bottom is individual. It's there's slope of 1.
It's just spread out.
Oh yeah, take a look at the grid lines. Every 2 boxes is 1 here. Every 1 box is 1 here. So it turns out to be 1 as a slope. Instead of counting up and over, which is what I did when you said 1/2 also, it's up 1 meter per second for every second. So it is 1 over 1. Thank you. Now, what are my units? What are my units here? What are my units? Yeah?
Meters per second in seconds.
Say it one more time.
So, meters per second in seconds, so it's meters per second squared.
Good. Meters per second. I like that. Good. Because the unit of the top one is meters per second over seconds, which really means this unit is 1 meter per second squared. And I might stop writing m for slope because it's very confusing in physics because m is mass and meters. So for now, I'm going to write the word slope. I realize that it might become confusing if you're looking at your notes later on, seeing m in multiple spots. So the slope is 1 meter per second squared, or 1 meter per second every second. Again, the velocity is changing by 1 meter per second every second. If your velocity is changing, what must you be doing? We haven't gotten to this yet because you guys are good though. I'm throwing these ideas out to these words. What must you be doing if your velocity is changing? What must you be doing? It's a one-word answer. What must you be doing? Accelerating. Very good. So this graph represents accelerated motion. And this is the acceleration right here. And we're going to get to that again in chapter 2, but see how the summary sign and the simple graph analysis can lead you to these ideas. This is your unit for acceleration. We're going to see this here. All right, very good. Very good.
Like, in logic, you understand meters per second.
So, yeah, that's a great question. So, what it's doing is this. Here's my velocity. Let's say my velocity is 0.5 meter per second, right? And then I start accelerating every second, getting faster. It would mean that I'm literally speeding up as I go across. So I might start really slow, get faster, get faster, get faster, get faster. But you're continuously getting faster. You're not moving at a constant rate. You're not finding, or you're not reaching a maximum speed and topping out. This is continuously getting faster. By how much is it getting faster? A meter per second every single second along the way. So every time a second elapses, the person's velocity is 1 more than it was before that. So this is the change in velocity, which is 1 every second, which is 1. Up 1, over 1, up 1, over 1 each time. We're going to get to acceleration in like probably 2 or 3 classes, and I'll go into a lot more of that, and we're going to start using probes to measure your motion and see it. So I'll go through all that again for sure. Okay?
You said that I understand the velocity is increasing, but the slope is constant, right? Or-
The slope is constant, yeah. And the slope represents acceleration in this graph. The slope of the velocity time graph is the object's acceleration, whereas a minute ago, the slope of the other one was the velocity. So we're going to see how slope is going to play a large role in physics and in calculus. Okay? Good question. Please ask. Yeah, Jack.
Does this mean if you put this set of data from a velocity time graph onto a distance time graph, it would be exponential?
Not exponential, parabolic. It looks like an exponential function, but it's not exponential.
Oh yeah.
Exponential growth
on
is
the
far
positive
greater.
side, it would be exponential.
No. So exponential growth is this is something you're going to learn in pre-calc this year. Exponential growth looks just like a y equals x squared curve. Y equals x squared is a parabola, right? But exponential growth rises at a greater rate than x squared.
Okay.
E to the x or 2 to the x or 3 to the x, those are exponential growth functions. Those increase at a greater rate than x squared does. So this is not exponential growth, it is parabolic growth for distance is what you're asking.
Okay.
Parabolic. It would be y equals x squared would be the function. Okay? All right, very good questions. For the last page, all I want to do is give the answers to save time and then ask you guys questions. The graphs were a little bit different. I wanted to make sure that you understood them and visually understood them. And at the same time, I wanted to point out that slope calculation where you should really try and use 2 points that are on the actual grid lines to help you. All right, I'm just going to read the answers. I don't have them written down here. Anybody want to tell me what they got for number 11? For 11, Caroline.
3 hours and 45 minutes.
3 hours and
45 minutes.
agree, disagree? Agree? I'm opening up my solution I wrote here. Hold on. Instead of redoing the problem. 3 hours and 45 minutes. Perfect. I got 3.75 I wrote down, which is 3 hours and 45 minutes. You should absolutely be able to convert between minutes and fractions of an hour. So if I have 40 minutes, how much of an hour is 40 minutes? 2/3 of an hour. 0.6666 repeating, right? You should know your fractions of an hour. Really, you should know your thirds of an hour, your half hours, and your quarter hours. Besides that, we just use general conversion factors, which we're going to learn about today, actually, in chapter 1. Yeah, go for it.
107.5 meters.
Yep, 12 is 107.5 meters. Very good, Valentina. How about 13, Regina?
160 gallons.
Good, 160 gallons. This is a rate problem, right? Starting value, losing some. 14, Jack?
48 feet per second.
Good, 48 feet per second. So in this case, we're taking a look at unaccelerated motion. We assume that there is no gravity accelerating this person downward. How do we know that, by the way? Because look at number 14. Look at the nature of the problem. It says a skydiver falls, right? When you fall to the ground, you might not know this yet, haven't gone through this. When you drop an object, what does it do as it falls, really? What does it really do?
Speeds up.
It speeds up, accelerates downward. So this example is making a wild assumption that there isn't gravity, or that the object has reached what?
Terminal velocity.
Nice, Jack, good word. Terminal velocity. Nice, I saw a couple hands pop up, very good. That's a phrase that we're going to use this year for sure. Terminal velocity is the idea like with a parachute, right? Or skydiver. They hit the parachute, and what happens? They slow down, right? And then ever see a person with a parachute come down, but they coast down nicely? They're moving at a constant velocity. Because the resistance of the parachute equals the weight of the object. So it's a balance of forces. We'll get to that in chapter 3, but very good. Number 15, Julia. Yes, she will make it. Good. How did you now analyze it? Did you find the distance traveled? Did you find the time it takes her? And what did you get for the time it takes her?
2.36 hours.
All right, and 2.36 hours is less than 2 hours and 30 minutes. Please be careful, because 2.36 hours, you might think 2 hours and 36 minutes, because 2.36. But this is really 2.5 hours, right? So 2.5 hours is more than enough time if she makes it in 2.36 hours. You could have done it another way. Did anyone do it differently? Valentina, what'd you do?
The distance.
Yeah.
She traveled, yeah, I did this, I got 27.5.
Yeah, in 2.5 hours, she'll travel 27.5 miles. So she'll make the full 26 miles. Okay, the full marathon. Number 16, Justin.
280 miles.
Very good. For this one, you break it into how many parts? How many parts? 3 parts of this problem, right? Number 16, we have 3 different segments. The first 2 hours, the next hour, and the final 2 hours. So 3 different parts. This is a piecewise function. Have you used that phrase yet?
Yeah.
Piecewise? I know in my class. In
Yeah,
Greek out?
I guess we got.
Fiore, yes. This is great. So I love how this course parallels pre-calc and then AP Calc parallels AP Physics. We're doing stuff in AP Physics right now, and I'm like a little bit ahead of AP Calc class, and they're like, oh yeah, we learned that in your class, and we use it the next time. So they're very similar notes. Good. So this is a piecewise function with 3 different slopes. Take a look. I'm gonna graphically show you what this is. 55 miles per hour for 2 hours. Then change the slope, increase 70 miles an hour for 1 hour. Then only 50 miles an hour for the last 2. So what we're seeing is a slope that changes for each piece of this function. The slope is represented by the speed in the problem. The speed in the problem. Last but not least, Mauro, go for it.
His average speed while jogging is 4 miles per hour.
So A is definitely 4 miles per hour. Agreed. Someone else for part B? For part B, Christina?
1:30 p.m.
Good. 1:30 p.m. Again, recognizing how to sum together times. It will take an hour and 15 minutes. An hour and 15 minutes on top of 12:15 is definitely 1:30 p.m. Okay? Any questions beyond this? This is the last page.
I was supposed to get out number 10. I just don't understand,
Throughout the year, make sure that you continue to do this. Continue to ask questions as we do things that are not obviously clear all the time.